Every choice you make might be creating another universe. The multiverse is a serious scientific frontier, not just a fantasy. Physicist Brian Greene calls it a natural extension of our best theories. By the end of this, you will understand how science is hunting for evidence of realities beyond our own and what it means for your place in the cosmos. We will uncover why the laws of physics might be a cosmic accident, and if the echo of a collision with another universe is hiding in ancient light. How would your life feel if you knew it was just one version of an infinite story? The idea of countless worlds did not begin in a modern laboratory. Over 2,000 years ago, the Greek philosopher Democritus stared into the night sky and proposed a stunning vision. He and his fellow atomists believed in an infinite void, a great emptiness where an endless number of worlds formed, existed, and dissolved by pure chance. They had no telescopes, no particle accelerators, only the raw power of logical thought. This ancient spark of pluralism flickered through the centuries, kept alive by thinkers who dared to look beyond a single creation. The German polymath Gottfried Wilhelm Leibniz argued for a universe filled with all possible realities, each one logically consistent but differing in its details. Much later, the psychologist and philosopher William James gave this idea a name, calling it a pluralistic universe. He suggested that our cosmos might be just one neighborhood in a vast metropolis of existence. Imagine a library so immense it holds every book that could ever be written. Some volumes are masterpieces, others are nonsensical, and many are simply different versions of the same story. This library represents the philosophical concept of plenitude, the notion that every possible form of reality must, in some sense, exist. If thinkers from antiquity could conceive of multiple worlds using nothing but reason, what does that reveal about the human mind's capacity to reach beyond the visible? Philosopher Nick Bostrom reminds us that the multiverse is not a new idea, but a very old one that has been rediscovered in a scientific context. This long intellectual heritage, a fascination with the unseen and the possible, laid the essential groundwork. It created a space in our collective imagination, a readiness for the moment when pure speculation would meet the hard mathematics of physics. That single electron, existing in multiple places until you look, is more than a laboratory curiosity. It is a direct challenge to our everyday experience of reality. In 1957, a young physicist named Hugh Everett proposed a radical answer to this quantum weirdness. His many worlds interpretation boldly stated that every possible outcome of a quantum event does not just have a probability, it actually happens. When a particle can go left or right, the universe does not choose. It splits in two, creating one reality where it went left and another, equally real, where it went right. This was not magic, but a mathematical consequence of taking the equations of quantum mechanics at face value, without adding the strange idea that observation collapses possibilities into a single fact. As physicist David Deutsch later put it, the multiverse is not a theory in itself. It is a consequence of our best theories. But if the universe is constantly branching, why do we only perceive one smooth, consistent timeline? The answer may lie in a process called wave function decoherence. Think of it like tuning a radio. All the radio stations are broadcasting at once, a chaotic superposition of every song and voice. Your radio, by tuning to one specific frequency, decoheres that one signal from the noise, making it clear and real to you, while the others simply fade into a background you cannot hear. In the same way, our reality is just one station we are tuned into, while countless other versions of events play on simultaneously, forever separated from our perception. This reframes the famous Schrödinger's cat thought experiment entirely. The cat is not both alive and dead in a single, paradoxical box. Instead, the moment the quantum trigger is activated, the universe splits. In one branch, a relieved scientist opens the box to find a living, purring cat. In another, a parallel version of that same scientist confronts a tragic outcome. Both events are equally real. So what does this mean for you, for the choices you make and the life you live? If every decision with a quantum element spawns new worlds, then there is a version of you who took that different job, who said yes instead of no, who turned left instead of right. Your identity is not a single thread, but a vast, branching tapestry of possibilities. This quantum view presents a reality in a state of constant, infinite creation, a concept that finds a strange and powerful partner in the story of our cosmos's own explosive beginning. The branching realities of quantum mechanics offer a dizzying view of a splintering cosmos, but there is another, even vaster engine of creation at work. This second pillar of the multiverse emerged not from the subatomic realm, but from our attempt to understand the very first moments of everything. The Big Bang was not a solitary explosion in a void. Instead, imagine a tiny primordial patch of space-time, smaller than a single atom, suddenly subjected to a violent, exponential growth spurt. In a fraction of a second, this patch ballooned to a size larger than our entire observable universe. This is the theory of cosmic inflation, and it solves many of the cosmos's deepest puzzles, like why the universe appears so uniform in all directions. But this theory contains a staggering implication. According to the concept of eternal inflation, this explosive process may never have completely stopped. While it ended in our local region of space, allowing galaxies and stars to form, the inflationary field that drove it continues to expand elsewhere at an unimaginable rate. Think of a pot of boiling water with bubbles constantly forming, expanding, and merging. In this cosmic foam, each bubble is not a pocket of air, but an entire separate universe, born from its own localized Big Bang event. The father of inflation theory, Alan Guth, noted the profound consequence, stating that it is surprisingly hard to build a model of inflation that does not inevitably lead to a multiverse. This perpetual creation is driven by a specific kind of energy, a scalar field often called the inflaton. Picture this field as a kind of cosmic fuel, a background energy that permeates the fabric of reality. When this fuel is abundant, space undergoes its frantic, inflationary expansion. But this field is not perfectly smooth. It is subject to tiny, random quantum jitters, fluctuations at the smallest scales. During inflation, these microscopic wrinkles are stretched to astronomical proportions. These stretched-out quantum ripples became the gravitational seeds for everything we see today. The slight over-densities that, over billions of years, collapsed under their own gravity to form the vast cosmic web of galaxies and galaxy clusters. But here is the truly mind-bending part. Those same quantum fluctuations can do more than just seed galaxies. In the eternally inflating background, a particularly large fluctuation can cause a local region of the inflaton field to drop to a lower energy state, like a bubble of steam suddenly condensing in the superheated water. This drop in energy halts inflation inside that bubble, and that region becomes a new, isolated pocket universe, forever disconnected from our own. And just as the initial conditions in our bubble gave us our specific laws of physics, other bubbles could have crystallized with entirely different fundamental constants. What if, in another bubble, the force of gravity was 1 trillion times stronger, instantly crushing any potential for structure? Or what if the nuclear forces were too weak to bind protons and neutrons, leaving that universe a forever diffuse, stillborn cloud of elementary particles. This is the landscape of possible universes, a vast and varied terrain of physical realities predicted by eternal inflation. It suggests that our universe, with its life-friendly rules, is not a special creation, but simply one fertile valley in an endless cosmic archipelago. This concept of a landscape finds its most detailed map not in inflation alone, but in the most ambitious attempt to unify all of physics, a framework known as string theory. String theory takes the idea of a cosmic landscape and gives it a breathtaking mathematical form. It proposes that the fundamental building blocks of our universe are not tiny, shapeless points, but unimaginably small, vibrating loops of energy. Think of a single, minuscule violin string. Played one way, it produces the note for an electron. Played another way, the same string creates a quark or a photon. Brian Greene explains this elegantly, stating that string theory suggests the universe is built from these tiny, vibrating strings, and the way they vibrate gives rise to all of nature's particles and forces. But for this beautiful symphony of physics to work, the mathematics demands something extraordinary. Our familiar 3 dimensions of space are not enough. The equations only balance if there are extra, hidden spatial dimensions curled up into shapes so small we could never hope to see them. These are not dimensions you can travel through. They are the intricate, multi-dimensional geometric forms known as Calabi-Yau manifolds. The specific, exact shape of one of these Calabi-Yau spaces at every single location in our universe is what determines the very laws of physics we experience. It dictates the mass of an electron, the strength of gravity, and the number of fundamental forces. This is where the concept of a multiverse blossoms into an almost ungraspable scale. Physicists have discovered that string theory does not point to one unique set of laws. Instead, it may allow for a number of possible stable configurations so vast it defies human comprehension. We are talking about 10 to the power of 500 different possibilities. That number is so large it has more digits than there are atoms in our entire observable universe. This is the string theory landscape, a cosmic catalogue of possible realities, each with its own unique entry in the laws of physics. Some versions of the theory even suggest our entire cosmos is a 3-dimensional membrane, or brane for short, floating within a higher dimensional expanse called the bulk. Our universe could be one page in an infinite, multidimensional book, utterly unaware of the other pages stacked next to it. So what does this mean for our particular set of physical laws? Imagine a giant cosmic radio dial, with each possible station representing a different universe with a different set of constants. One station might play the harsh, fast music of a universe where stars burn out in 1,000,000 years. Another might offer only the silent, empty hiss of a cosmos where matter never coalesced. We exist in the one narrow band where the station comes in clear, where the laws are perfectly tuned for complexity, for planets, and for life. If our universe's laws are just one random setting on this cosmic dial, does that make them less special or more fortuitous? This question leads us directly to one of the most debated ideas in modern cosmology, a principle that attempts to explain why we find ourselves in such a seemingly fine-tuned reality. The universe's fundamental forces appear perfectly balanced for our existence, a cosmic coincidence so precise it demands an explanation. If gravity's pull were just a fraction stronger, the entire cosmos would have collapsed back on itself shortly after the Big Bang. If the nuclear forces that bind atoms were even slightly weaker, stars could never have ignited. This delicate balance is known as the fine-tuning problem, and it presents a profound puzzle. Why does our universe seem custom-made for life? A powerful yet controversial answer comes from a concept called the Anthropic Principle. The physicist Brandon Carter, who named the idea, framed it with a crucial insight. What we can expect to observe must be restricted by the conditions necessary for our presence as observers. In its simplest form, the weak anthropic principle is almost a truism. It states that we must find ourselves in a universe capable of supporting conscious life, because we are here to observe it. This is not a claim about why the universe is this way, but a recognition of a basic selection effect. A puddle of water, perfectly conforming to the shape of the hole it sits in, might marvel at how exquisitely the hole fits its form. The puddle does not realize it is the one that has adapted to the pre-existing cavity. In the same way, we are the puddle and our universe is the hole. We exist because the physical constants are right for us, not the other way around. This weak version is a logical tool, a way of filtering our expectations, but there is a stronger, more speculative version. The strong anthropic principle suggests the universe must have properties that allow life to develop at some stage in its history. This statement edges toward a sense of purpose or design, a universe compelled to produce observers. The distinction is critical. One is a statement of our inevitable location in a vast cosmic landscape. The other hints at a deeper law or necessity. Consider the cosmological constant, the energy density of empty space. Its observed value is astonishingly small, yet if it were even slightly larger, the universe would have expanded so rapidly that no galaxies or stars could ever have formed. The odds of this constant having the value we measure by pure chance are virtually zero, yet here we are, in a single, solitary universe. This seems like a miracle. But in a multiverse, an infinite tapestry of bubbles, each with different physical laws, it becomes a statistical certainty. Somewhere in that vast ensemble, a few universes will, by pure chance, have the right numbers for life. We could not exist in any of the others. Does this principle truly explain the fine-tuning, or does it merely sidestep the question by invoking an unobservable infinity? It transforms a why question into a where question. We are not asking why the universe is fit for life, but where, in the expanse of all possibilities, life-permitting universes can be found. This philosophical tool offers a way to navigate the staggering implications of the multiverse, but it leaves us with a deeper hunger, a need to move beyond pure reasoning and find something tangible. If these other realities are more than mathematical ghosts, where could we possibly look for their fingerprints? The hunt for a cosmic fingerprint begins with the oldest photograph in existence. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, faint hiss in their giant horn antenna in New Jersey. They scrubbed away pigeon droppings and checked every connection, but the noise remained, a constant static coming from every direction in the sky. They had accidentally discovered the cosmic microwave background, the cooled remnant of the Big Bang's first fireball, a ghostly echo from the birth of the universe. This faint glow is our most direct window into the primordial cosmos, a snapshot from a time when the universe was just a hot, dense plasma. Today, powerful space telescopes like WMAP and Planck have mapped this afterglow in exquisite detail, revealing a nearly uniform tapestry of temperature. But woven into that tapestry are strange, unexpected threads. One of the most compelling is a mysterious cold spot, a vast region of space significantly cooler than its surroundings. To some cosmologists, this is not just a random fluctuation. It could be a cosmic bruise, the imprint of a collision with another bubble universe in the multiverse. The physicist Laura Mersini-Horton has championed this idea, stating that the anomalies in the WMAP and Planck data could be the first experimental evidence for the existence of other universes. How could a collision leave a mark? Picture the fabric of our universe as the still surface of a pond. If another universe, a separate bubble of reality, bumped against ours in the distant past, it would be like a stone thrown into that pond. The impact would send a specific pattern of ripples radiating outward, a concentric ring of temperature and polarization differences frozen into the cosmic microwave background. This is the kind of signature scientists are meticulously searching for in the data. Other anomalies also tantalize researchers, such as the so-called axis of evil, a strange alignment of large-scale features in the CMB that seems to defy the standard model's prediction of universal randomness. Could these be subtle shadows cast by neighboring realities, warping our cosmos from the outside? If we one day found definitive proof of a collision in this ancient light, it would shatter our cosmic isolation forever. We would know that our universe is not a solitary island, but one shoreline among countless others in a vast, intersecting ocean of realities. While the CMB offers a look into the deep past, another form of evidence could come from ripples in the very fabric of space and time. If the cosmic microwave background is a fossilized photograph of the infant universe, then gravitational waves are its first cries, a vibration that has been ringing through the cosmos since the beginning. These are not waves of light or sound, but literal ripples in the fabric of space and time itself, generated by the most violent cosmic events. When the universe was born in a flash of inflation, that explosive stretching of space-time should have sent powerful tremors through reality, a primordial gravitational wave background that still permeates everything. As a LIGO researcher once noted, gravitational waves are a new messenger, allowing us to hear the universe in a way we never could before. While our current observatories like LIGO listen for the loud chirps of black holes colliding, the next generation of detectors is being designed to hear something far more subtle and profound. The planned space-based LISA mission will be a trio of satellites flying in a perfect triangle millions of kilometers apart, using lasers to measure minute distortions in space. Its goal is to tune into the faint, constant hum of this primordial background, a signal that is not a single event but the collective rumble of creation. The characteristics of this hum, its spectrum and amplitude, are a direct record of the energy that drove inflation. It is a fossil imprint of the inflattened field itself, the very engine of the multiverse. The strength of these waves would tell us just how powerful that initial burst was, and whether the conditions for eternal inflation and perpetual bubble universe creation were truly met. Picture this not as listening for a single note, but for the collective roar of an ocean. Each bubble universe popping into existence in the eternally inflating sea would contribute its own tiny vibration to this cosmic symphony. Detecting this stochastic background would be like hearing the faint, collective hum of all those other realities being born. So what would it mean if we one day decoded this signal and found a signature that defied all conventional explanation? What if the pattern of ripples pointed to a pre-Big Bang event or bore the scar of a collision with another cosmic domain? Such a discovery would do more than confirm inflation. It would open a window into the physics that generates the multiverse, showing us that our universe is just one note in an infinite cosmic chord. This shifts the entire endeavor from a theoretical puzzle to a tangible hunt, pushing our investigative tools beyond the limits of light and into a new era of multi-messenger astronomy, where we listen for the echoes of realities we may never see. The ultimate expression of the multiverse idea strips away everything familiar, leaving only the cold, beautiful skeleton of mathematics. Physicist Max Tegmark proposes a hypothesis so radical it redefines reality itself. He suggests that our external physical reality is not just described by mathematics, but that it is in fact a mathematical structure. This is the mathematical universe, a level 4 multiverse where existence requires no stars, no atoms, not even space or time as we know them. All that is needed is a consistent set of abstract mathematical rules. A mathematical structure is simply a set of abstract entities and the formal rules that govern their relationships. This could be as simple as the geometry of a perfect circle, the moves in a game of chess, or the complex differential equations that describe the curvature of spacetime in Einstein's general relativity. In Tegmark's view, if you can describe a universe with a consistent set of mathematical rules, then that universe is not a hypothetical model. It is physically real somewhere in the ultimate ensemble of all possible structures. This is a profound departure from the other multiverse levels. The level 1 multiverse is just more space like ours, far beyond our cosmic horizon. Level 2 consists of bubble universes born from eternal inflation, each with different physical constants. Level 3 encompasses the branching realities of quantum mechanics, but Level 4 includes all of these and infinitely more. It contains universes governed by laws we have not yet imagined, structures with 11 fundamental forces, or realities where time flows in 2 directions. It even includes a universe that operates on the simple, deterministic rules of Conway's game of life. In that mathematical reality, complex patterns of gliders and blinkers would emerge, and from their perspective, their 2-dimensional grid world would be just as real and concrete as our own 4-dimensional spacetime. This idea offers a stunning explanation for a deep mystery that has puzzled physicists for generations: the unreasonable effectiveness of mathematics in the natural sciences. Why do the laws of physics, discovered through observation and experiment, so perfectly align with intricate mathematical truths discovered through pure thought? The answer, according to this hypothesis, is simple and breathtaking. We are not inventing mathematics to describe our world. We are merely discovering the particular mathematical structure that we happen to inhabit. Mathematics was not created by humans. It was discovered because it is the fundamental substance of reality. This forces a deeply unsettling question upon us. If every mathematically possible story is true in some universe, from a world ruled by the rules of Sudoku to one where gravity repels, what meaning remains for the words truth and existence? In this ultimate pluralistic vision, nothing is hypothetical. Every fantasy, every nightmare, every logical possibility is playing out in a reality just as valid as our own. Our consciousness, our sense of self, becomes a specific pattern within one particular mathematical structure, a temporary configuration in an infinite and eternal landscape of abstract forms. This is the logical extreme of the multiverse, a concept that pushes our understanding of what is real to the absolute breaking point. So where does that leave you, the observer? The very act of looking at the world seems to force it into a single, definite state, but the multiverse suggests this is an illusion. This brings us to one of the most profound puzzles in all of science, the role of consciousness itself. Does your mind somehow collapse the quantum wave function into one reality, or does your conscious experience simply flow along a single branch in an infinite tree of possibilities? The traditional Copenhagen interpretation of quantum mechanics, developed in the 1920s, seemed to give consciousness a special, almost magical role. In this view, a quantum system exists in a blurry superposition of all possibilities until a conscious observer measures it, forcing it to choose a single outcome. This places the human mind at the center of the quantum drama, but the many worlds interpretation offers a starkly different picture. Here, there is no collapse. Every possible outcome physically occurs in its own branch. Your consciousness does not cause the split, it merely follows one path. You are not a director of the play, but an actor who only experiences the single scene you are in. completely unaware of all the other performances happening simultaneously. This leads to a bizarre paradox famously illustrated by the Wigner's friend thought experiment. Imagine a physicist, Wigner, outside a sealed laboratory. Inside, his friend conducts a quantum experiment, like measuring the spin of an electron, according to standard quantum rules, until Wigner opens the door and asks for the result. His friend inside the lab is in a superposition of having seen both possible outcomes. For Wigner, the entire laboratory, including his friend's mind, is in a blurry quantum state, but for the friend inside, the result was definite the moment he looked. So whose perspective is correct? Is the friend's consciousness in a superposition until observed by Wigner? This paradox highlights the profound difficulty of assigning a special role to consciousness. If consciousness collapses reality, then whose consciousness counts? Does a cat's, a bacterium's? To avoid this, many worlds removes the privilege entirely. In this view, the wave function never collapses. It only appears to collapse from our limited, branching perspective. What we call a measurement is just the process of a conscious observer becoming entangled with a quantum system. Before you look, there is one universe where you will see a live cat and one where you will see a dead cat. The moment you look, your own consciousness divides, each copy believing it saw a single, definite result. This creates a new challenge, the problem of probability. If every outcome happens, what does it mean to say one has a 90% chance and another only 10%? Your branching selves would all feel equally real. Some physicists suggest that the measure of existence, the number of branches where a particular you ends up, might replace the old idea of probability. Perhaps you are more likely to find yourself in a branch that was more probable according to the quantum math. Now, picture your own consciousness not as a single point, but as a vast, ancient tree. The roots and trunk represent all the possible versions of you, spreading deep and wide through the multiverse. But your moment-to-moment experience, your sense of self, is like a single leaf on one tiny branch, soaking up the sun and completely unaware of the immense structure that supports it. You feel like a continuous, singular person, but you are just one expression of a far grander entity. This brings us to a deeply reflective question. If your consciousness is constantly splintering across worlds with every quantum decision, is there a true, original you? Or are you simply the collection of all your possible selves, momentarily experiencing one thread of a sprawling tapestry? The physicist John Wheeler offered a different, equally mind-bending perspective with his concept of a participatory universe. He proposed that we are not just observers, but participators in bringing into being not only the near and here but the far away and long ago. In this view, our present acts of observation might somehow reach back in time and determine the past, including the very cosmic history that led to our existence. It is a loop of creation where the observers are an essential part of the machinery. This circles back to the most exotic ideas like panpsychism, which suggests that consciousness is not a product of complex brains but a fundamental property of the universe like mass or charge, present to some degree in every particle. In a multiverse, this would mean every branching reality is inherently conscious, just configured in different ways. The enigma of consciousness remains the central, unsolved mystery, a ghost in the cosmic machine that becomes infinitely more complex when viewed through the lens of intersecting realities. The line between a naturally born cosmos and an artificial one may be far thinner than we ever suspected. Another powerful route to a multiverse does not require infinite space or quantum branches, but simply an advanced civilization with immense computing power. This is the simulation hypothesis, the provocative idea that our universe, and perhaps every universe we have discussed, is an elaborate simulation running on a computer built by a hyper-advanced intelligence. Philosopher Nick Bostrom framed this possibility with stark clarity in his seminal paper, stating that if we are living in a simulation, then the cosmos that we are observing is just a tiny piece of the totality of physical existence. In this view, the totality is the base reality, the original universe where the powerful simulators reside, and our entire history from the Big Bang to this very moment is a generated construct, one of countless such simulations they have created. This reframes the entire multiverse concept from a feature of nature to a potential artifact of technology. Bostrom's argument rests on a compelling trilemma, a set of three propositions where at least one must be true. The first possibility is that almost every civilization at our level of development goes extinct before it reaches the technological maturity to create realistic simulations. The second is that even if they survive, they universally lose interest in running such ancestor simulations, perhaps deeming it unethical or pointless. The third and most startling is that we are almost certainly living in a simulation right now. The logic is simple. If even one civilization avoids extinction and chooses to run a vast number of simulations, the number of simulated minds would utterly dwarf the number of original, base reality minds. Therefore, if you are a conscious being, the statistical probability is that you are one of the simulated ones. This is not a proof, but a stark statistical likelihood. If our reality is simulated, might there be glitches in the code, shortcuts taken by the programmers? Some physicists speculate that we could find signatures of the simulation in the fundamental laws of physics. Perhaps at the very highest energies, the smooth continuum of space-time breaks down into a pixelated grid, revealing a fundamental computational limit. Maybe there are mathematical inconsistencies or rounding errors buried in the constants of nature, like a cosmic programmer taking a shortcut to save processing power. Think of a sophisticated video game like The Sims. The characters within that game experience their world as real. They have loves, ambitions, and daily routines, completely unaware that their entire existence is confined to a machine, governed by code written by an intelligence they cannot perceive. Their physics are simplified, their world bounded. From our perspective, their reality is a construct, but from within the simulation, it is the only reality they have ever known. This forces a deeply personal question. If we one day discovered incontrovertible proof that we were living in a simulation, would that knowledge make your life, your loves, and your struggles any less real? The emotions you feel, the connections you forge, the beauty of a sunset, these experiences have a reality to you regardless of their ultimate origin. The simulation hypothesis blurs the final boundary, transforming the multiverse from a cosmic principle into a potential technological artifact. It suggests that our universe could be one entry in an infinite library of simulated worlds, each with its own slightly tweaked physical laws, created not by random quantum fluctuation but by deliberate design. This staggering idea propels us toward the final, most practical question of all. If these other realities exist, either as parallel branches, cosmic bubbles, or simulated constructs, could we ever hope to interact with them? A theory that cannot be proven wrong is not science at all. This is the razor-sharp principle of falsifiability, famously articulated by philosopher Karl Popper, who stated that a theory which is not refutable by any conceivable event is non-scientific. It is a cornerstone of the scientific method, and it poses the single greatest challenge to the entire multiverse concept. If we can never visit another universe, never directly observe another bubble or quantum branch, how can we possibly prove the idea wrong? Does this relegate the multiverse to the realm of untestable metaphysics, a captivating story but not a legitimate scientific theory? This criticism strikes at the very heart of the endeavor, forcing us to ask where we draw the line between groundbreaking science and pure speculation. The defense, however, lies in the power of indirect evidence. While we may never touch another reality, we can look for its fingerprints in our own. The search for specific, anomalous patterns in the cosmic microwave background, like the precise concentric rings that would signal a bubble collision, is a prime example. This is not a vague hunt for anything strange. It is a specific, falsifiable prediction made by certain multiverse models. If we scan the entire sky and find no such patterns, that particular version of the multiverse theory would be dealt a severe, perhaps fatal, blow. Similarly, the precise spectrum of primordial gravitational waves, which future observatories hope to detect, could either support or rule out the inflationary models that inevitably lead to an eternal universe-spawning process. Some versions of string theory also make predictions about the specific value of the cosmological constant or the number of fundamental particle families, predictions that could, in principle, be tested against increasingly precise astronomical data. This contrasts sharply with the more abstract mathematical multiverse, which, by encompassing all possible structures, risks becoming immune to falsification. If every possible outcome exists somewhere, then no observation can contradict the theory. This is the fine line scientists must walk. History offers a powerful lesson here. The theory of continental drift proposed by Alfred Wegener was initially dismissed by many as untestable speculation. How could entire continents possibly move? Without a known mechanism, it seemed like just an interesting idea. Decades later, the discovery of plate tectonics provided that mechanism and the hard, physical evidence that transformed a fringe concept into foundational geology. The multiverse may be in a similar adolescent stage, waiting for its plate tectonics moment, for a new form of evidence or a deeper theoretical framework that connects its grand vision to tangible, measurable consequences. So we are left with a profound and necessary tension. Should we allow our scientific theories to explore realms beyond our current observational reach, trusting that indirect evidence and future technological leaps will eventually provide validation? Or does venturing into the permanently unobservable risk undermining the empirical foundation that makes science so powerful? This is not merely a debate about parallel universes, but a struggle to define the boundaries of knowledge itself. Your favorite superheroes have been wrestling with the multiverse for decades. Long before physicists debated quantum branches, comic book writers were sending their characters crashing through dimensional barriers, exploring worlds where one different choice changed everything. This cultural takeover, from the pages of Marvel and DC to the biggest films of our time, has done more than just entertain us. It has fundamentally reshaped how the public understands these staggering scientific ideas, simplifying the complex, dramatizing the abstract, and sometimes taking creative liberties that a physicist might wince at. These stories act as a modern mythology, a vast playground where we can explore the deepest questions about identity, choice, and destiny on a scale we can emotionally grasp. In Marvel's Doctor Strange in the Multiverse of Madness, the multiverse is a chaotic, psychedelic realm of infinite possibilities, a clear nod to the many worlds interpretation. The film visualizes the act of branching, showing America Chavez jumping between realities, each a distinct timeline where events unfolded differently. Similarly, Spider-Man No Way Home brings together three different versions of Peter Parker, each shaped by their unique struggles and losses. This portrayal brilliantly illustrates a core philosophical implication of the multiverse, that your identity is not a single, fixed story, but is profoundly shaped by your context and your wounds. Yet, these stories often simplify the mechanics. They frequently present characters consciously traveling between branches, a feat that most scientific models consider impossible due to the sheer decoherence that separates one reality from another. In the real many worlds theory, you do not hop between branches, you simply become multiple versions of yourself, each unaware of the others. A more nuanced exploration comes from the film Everything Everywhere All at Once. Here, the multiverse is not about epic superhero battles, but about the quiet desperation of a single, overwhelmed woman. The concept of verse jumping, of tapping into the skills and memories of your other selves, serves as a powerful metaphor for regret, potential, and the paths not taken. The film's bizarre and hilarious scenarios, like a universe where people have hot dogs for fingers, highlight the sheer randomness of cosmic possibility, mirroring the string theory landscape's 10 to the 500th power different physical laws. It grounds the infinite in the deeply personal, asking what meaning our choices have if every possible choice is made somewhere. This theme of alternative selves has been a staple of science fiction for generations. The original Star Trek series introduced the Mirror Universe, a dark reflection of the Federation where humanity is a brutal, fascistic empire. This was never about accurate physics. It was a narrative device to explore the nature of evil. It asked a terrifying question: are you a product of your innate character, or simply a result of your environment? In the Mirror Universe, a noble captain is a ruthless tyrant, suggesting that the line between good and evil might be thinner than we think, a matter of circumstance rather than essence. So, does seeing the multiverse play out on the silver screen make these ideas feel more tangible and plausible, or does the spectacle risk trivializing the profound scientific quest? There is no simple answer. On one hand, these stories spark a vital public curiosity. A viewer leaving a Spider-Man movie might for the first time look up the real many worlds interpretation, creating a bridge between pop culture and real science. The dramatic stakes make the abstract philosophy feel immediate and personal. On the other hand, the focus on conscious travel and universe-saving plots can create misconceptions, making a deeply strange and counterintuitive concept seem like just another form of interstellar travel. This cultural permeation is a testament to the multiverse's powerful grip on the human imagination. It shows that these are not just cold equations on a blackboard, but narratives that speak to our core anxieties and hopes about who we are and what we might have been. This widespread fascination, in turn, fuels scientific curiosity, funding, and a new generation of thinkers who first encountered these ideas not in a textbook, but in a theater, wondering if somewhere out there, another version of them is doing the very same thing. The solid ground of your own identity begins to feel like shifting sand. If every choice spawns a new universe, then the person you are right now is just one single thread in an infinite tapestry of selves. This confronts us with a deep philosophical earthquake, shaking the foundations of morality, regret, and the very meaning of responsibility. Think about a moment of profound regret in your own life, a path not taken. The multiverse suggests there is a version of you who did take that path, who is living out the consequences of that other decision. So what weight does your regret truly hold? This line of thinking can lead to a dangerous form of existential nihilism. If every action is taken somewhere, then no single action in your own branch seems to matter. Your failures are balanced by another version's success, your pain by another's joy. Why strive for anything if a version of you has already achieved it? Yet, there is a radically different perspective, one of profound acceptance. It suggests that liberation lies in releasing the paralyzing anxiety of perfection, in knowing that the path you are on is uniquely yours to experience, even as others are walked by other versions of you. The philosopher Derek Parfit challenged our conventional view of self, arguing that we are not separately existing entities apart from our brains and bodies. He proposed that personal identity is not a deep, further fact, but is based on psychological connectedness over time. In a branching multiverse, this idea is stretched to its absolute limit. Are all these versions of you still, in any meaningful sense, you, or are they simply other people who share your initial history? This fractures the very concept of a singular soul. This leads to one of the most unsettling thought experiments in quantum theory, the idea of quantum immortality. Imagine you are part of a dangerous experiment where a quantum trigger has a 50% chance of firing a lethal bullet. In the many worlds interpretation, the universe splits. In one branch you die, but in the other branch you survive. From your subjective perspective, you only experience the branches where you continue to exist. It would seem as though you are miraculously surviving against all odds, over and over again, while the versions of you in the other branches perish. Of course, this is a deeply flawed and macabre fantasy, as your conscious experience is tied to one specific branch and would end there, but it highlights the bizarre implications for personal continuity. Now, apply this to ethics. Consider the framework of utilitarianism, which seeks to maximize happiness and minimize suffering for the greatest number of people. How do you calculate that across a near-infinite multiverse? If you make a selfish choice that causes suffering, is that action morally neutral because in a parallel branch, a selfless version of you created an equal amount of joy? This feels like a moral cop-out. It suggests that our ethical obligations might be local, confined only to the specific reality we inhabit and the beings within it. Your responsibility is to the world you can directly affect, so here is the ultimate question for you to carry forward. Does the knowledge that every possible version of you exists make the life you are living feel less significant, like a single drop in an infinite ocean? Or does it free you, granting you the courage to make bold choices without the crushing weight of wondering what might have been, because you can trust that what might have been, in a very real sense, already is? The hunt for the multiverse is accelerating, pushing our tools to the very edge of what is technically possible. This experimental frontier is where cosmic speculation meets the unforgiving test of data, and a new generation of observatories is being built to listen for whispers from beyond our universe. A project scientist for the upcoming Nancy Grace Roman Space Telescope captured this ambition perfectly, stating that they are designing telescopes not just to see farther, but to see the first moments of time more clearly. This is the new paradigm, moving from mapping the cosmos to forensically examining its birth certificate for signs of other creators. On the high, dry plateaus of the Atacama Desert in Chile, the Simons Observatory is already under construction, a forest of small, sensitive telescopes focused on a single goal, mapping the cosmic microwave background with a resolution 50 times greater than the Planck satellite. Its successor, the colossal CMB Stage 4 experiment, or CMB-S4, will be even more powerful, an array of 500,000 detectors scanning the sky from the South Pole and the Chilean Andes. These instruments are not just making a better picture, they are hunting for the specific, faint patterns that would be the undeniable signature of a bubble universe collision, a concentric bruise left in the ancient light. Simultaneously, in the quiet of space, a different kind of observatory is taking shape. The Laser Interferometer Space Antenna, LISA, will be a gravitational wave detector of unimaginable precision. 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by lasers, will listen for the low-frequency hum of the primordial gravitational wave background. This signal is the direct echo of inflation's violent expansion, and its character will tell us if the process was truly eternal, a perpetual engine for generating an infinite number of bubble universes. These colossal projects are complemented by smaller, but no less profound, experiments here on Earth. Next-generation particle accelerators, probing ever higher energies, could uncover particles that only make sense if they are vibrations from hidden, extra dimensions. And on laboratory tables, exquisitely controlled quantum experiments are searching for objects that behave as if they are interacting with unseen parallel realities, testing the limits of the many worlds interpretation. The coming decade is poised to become a golden age of cosmology, a period where a flood of new data will either confirm our most daring cosmic models or force us back to the drawing board. So we are left with a thrilling possibility. What if the next great discovery in physics is not a new particle, but the first direct evidence for a reality beyond our own? This is no longer science fiction, but the concrete mission of billion-dollar experiments, a global effort to answer one of humanity's oldest questions: are we alone in the cosmos, or are we just one voice in a choir of infinite echoes? The mathematical elegance of string theory presents a profound dilemma. For all its beauty in unifying gravity and quantum mechanics, it has yet to make a single prediction that can be tested in a laboratory. This is the theory's testability crisis, and it is deeply entangled with the very idea of the multiverse. The core of the problem lies in the string theory landscape, that staggering collection of 10 to the 500 possible stable configurations for the cosmos. With so many potential ways for a universe to exist, pinpointing one unique set of laws that must describe our own becomes nearly impossible. How can you test a theory that allows for almost everything? This has led prominent critics like physicist Peter Woit to level a damning charge that string theory is not even wrong. It is a phrase borrowed from the great Wolfgang Pauli, meaning an idea is so vague it cannot be falsified, placing it outside the realm of science altogether. On one side of this fierce debate, proponents argue the landscape is not a bug, but a brilliant feature. They see it as the only framework capable of naturally explaining the apparent fine-tuning of our universe through the Anthropic Principle. Our cosmos is not special, it is simply one that randomly ended up with the right constants for life, a single data point in a vast statistical ensemble. The other side views this as a catastrophic surrender. If the theory cannot tell us why the electron has its specific mass or why gravity is so weak, then it has failed in its primary goal to explain the world we actually see. They fear it has become a philosophical exercise, a captivating story detached from empirical reality. In response, some theorists are searching for a way out of this impasse. One promising direction is the swampland conjecture. This idea attempts to draw a clear boundary in the space of all possible physical laws. It suggests that while the string theory landscape is immense, it is not infinite. There exists a swampland of seemingly consistent theories that are actually incompatible with a full theory of quantum gravity. If true, this could dramatically shrink the number of possible universes, potentially restoring string theory's predictive power by ruling out whole classes of alternatives. Imagine the entire multiverse as a boundless, fog-shrouded ocean. We know we are on one island, our universe, with its specific laws of physics. The string theory landscape suggests there are countless other islands out there in the mist. But without a map or a boat, we have no way to visit them, to confirm their existence, or even to be sure the ocean is really there. We are left staring at the horizon, wondering if the patterns we see are real or just a trick of the light. This forces a deeply reflective question about the nature of science itself. If a theory is mathematically beautiful, internally consistent, and points toward a grander reality, but remains stubbornly silent in the face of experiment, should it still guide our search for fundamental truth? The fate of string theory and how we view the multiverse are two threads of the same rope, and the tension between them is pulling at the very definition of what it means to know something. Our three-dimensional reality might be an elaborate illusion, a cosmic mirage projected from a flat, two-dimensional surface. This is the staggering claim of the holographic principle, a radical idea born from the fiery paradoxes of black hole physics. When matter falls into a black hole, it seemingly vanishes, taking all its information with it. This violates a core tenet of quantum mechanics, which states that information can never be truly destroyed. Physicists Leonard Susskind and Gerard T. Hooft proposed a brilliant solution. They realized that all the information describing everything within a volume of space could be perfectly encoded on its two-dimensional boundary, like a movie being stored on a DVD. The event horizon of a black hole acts as that screen, storing a perfect pixelated record of everything that ever fell in. Susskind himself summarized this profound shift, stating that the three-dimensional world of ordinary experience may be a kind of illusion. We are not living inside the movie, we are the movie being projected from the edge of our cosmic sphere. This abstract concept found a concrete, mathematical form in a discovery known as the AD/CFT correspondence. It is a duality, a perfect dictionary that translates between two seemingly unrelated worlds. On one side, you have a universe with gravity, described by string theory, living in a warped space called anti-de Sitter space. On the other side, you have a quantum field theory without gravity, living on the flat, lower-dimensional boundary of that space. Every single event, every particle interaction, every gravitational tug within the bulk of that universe has a perfect, one-to-one translation into the complex interactions of quantum fields painted on its distant boundary wall. It is as if the entire rich, three-dimensional drama of a galaxy, with its stars and planets and swirling nebulae, is nothing more than a specific pattern of information vibrating on a vast celestial film canister. Now, the great challenge is that our universe is not an anti-de Sitter space. It is an expanding, de Sitter-like cosmos. Yet, the tantalizing possibility remains that a similar holographic description applies to us. If it does, it completely reframes the multiverse. All those bubble universes, quantum branches, and string theory landscapes might not be separate, physical places in a higher dimensional bulk. They could simply be different projections from a single, underlying information structure, a master hard drive of reality. Think of it like a movie theater with an infinite number of screens. Each screen shows a different film, a different universe with its own unique story and laws of physics, but all of them are being projected from the same bank of digital projectors, running off the same central server. The true reality is not the flickering images on the screens, but the immutable bits of data stored on that server. So if we are living in a hologram, a sophisticated projection, what does that imply for the reality of all those other universes we have been discussing? Are the parallel worlds of the quantum multiverse just other videos playing in a cosmic media library? Is the cosmic bubble bath of eternal inflation merely a collection of different projections from a single, unified source code? This principle suggests a profound unification, a potential master theory where all of existence, in all its bewildering variety, emerges from a fundamental layer of information. It asks us to consider that the deepest level of reality is not made of space, time, or matter, but of pure, abstract data. The multiverse, then, is not a place you could ever travel to. It is the ultimate collection of files, and we are just one of them, currently playing on the grand projector of existence. Dark energy is the silent, relentless force shaping our cosmic destiny. Its discovery in the late 1990s, which earned astronomers the Nobel Prize, revealed a stunning truth. the expansion of our universe is not slowing down, it is accelerating. This mysterious repulsive energy, comprising about 70% of the cosmos, is now the dominant player in our long-term future. Nobel laureate Adam Rees called it the most profound mystery in all of science, a puzzle that connects directly to the multiverse. The simplest form of dark energy is the cosmological constant, a fixed energy density woven into the fabric of empty space itself. Its value is absurdly small, yet if it were even slightly larger, galaxies would never have formed and life would be impossible. This precise fine-tuning is a cornerstone of the anthropic argument for the multiverse. In a single universe, such a perfect number seems miraculous. But in a landscape of infinite bubbles, it becomes a statistical necessity. We just happen to live in one of the rare bubbles where the value allows for a long, rich cosmic evolution. The specific strength of this dark energy dictates our universe's ultimate fate. If it remains constant, as the cosmological constant suggests, we are headed for a big freeze. Over trillions of years, galaxies will fly apart, stars will burn out, and space will become a cold, dark, and empty void. But if dark energy is not constant and instead grows stronger over time, a far more dramatic end awaits: the Big Rip. In this scenario, the repulsive force would eventually overcome all other forces, tearing apart galaxies, then solar systems, planets, and finally, the very atoms that constitute matter. There is a third, even more unsettling possibility rooted in quantum field theory: that our universe is not in its true, lowest energy state. It could be metastable, existing in a false vacuum, like a ball resting in a small dip on the side of a much deeper valley. A random quantum fluctuation could trigger a vacuum decay event, creating a bubble of true vacuum that expands at the speed of light, fundamentally rewriting the laws of physics in its wake and obliterating everything we know. Across the string theory landscape, the value of the cosmological constant is not a universal law, but a local bylaw. In other bubble universes, it takes on different values, leading to wildly different destinies. Imagine the multiverse as an immense, eternal garden. Some universes are like flowers that wither instantly, their dark energy so strong that space expands into a meaningless void before the first star can even ignite. Others are like stubborn weeds, their expansion so slow and gravitational collapse so swift that they crunch back down almost immediately. Our universe is one of the rare, beautiful blooms that lasts just long enough for complex structures like galaxies, stars, and conscious beings to emerge and appreciate the fleeting beauty. Is the accelerating expansion we observe a unique feature of our local cosmic neighborhood, or is it a common property woven throughout the entire multiversal landscape? The answer to that question holds the key to understanding not just our own end, but the very diversity and structure of reality on its grandest scale. The nature of dark energy is not merely about how our story ends. It is a fundamental clue to the architecture of all possible stories. Einstein famously dismissed quantum entanglement as spooky action at a distance, a phrase that betrayed his deep unease with the phenomenon. In our universe, when two particles become entangled, they lose their individual identities, becoming a single, unified quantum system. Measure the spin of one particle here, and you instantly know the spin of its partner, even if that partner is now on the other side of the galaxy. This connection seems to defy the cosmic speed limit of light, yet it cannot be used to send a message faster than light. It is a correlation, not a communication. But what if this spooky connection is not confined to our single reality? Some physicists propose that when particles become entangled, they are not just linked across space within our universe, but are, in fact, a single entity whose existence is smeared across multiple branches of the multiverse. The particle you measure here and its partner far away are two aspects of one thing, but that one thing has threads reaching into other realities. Physicist Sean Carroll frames this elegantly, stating that entanglement is a feature of the universe, not a bug. It is a fundamental property of how reality is woven together. This perspective finds a startling mathematical partner in a concept known as ER equals EPR. This proposal, championed by thinkers like Leonard Susskind, suggests that entanglement, the EPR part named for Einstein and his colleagues, is physically equivalent to the existence of a tiny, subatomic wormhole, an Einstein-Rosen bridge connecting the particles. In this view, the spooky action is not action at a distance at all, but a direct connection through a microscopic shortcut in the fabric of spacetime. Now extend this idea into the many worlds interpretation. If every quantum possibility branches into a new universe, then perhaps the particles involved in an entanglement are not just in one branch. Their shared existence might be a bridge that gently tugs on the fabric of adjacent realities. The influence would be unimaginably faint, a whisper lost in the roar of decoherence, but in principle, it suggests a form of interaction. Imagine an entangled pair of electrons as a single, stretched-out entity, a cosmic worm whose head is in one universe and its tail in another. The decisions made in one branch could impart a minuscule, perhaps undetectable, nudge to its counterpart elsewhere. This is not about hopping between worlds, but about a deep, structural connectivity that binds the entire multiverse into a single, coherent quantum object. So we are left with a question that tests the limits of definition. If even the slightest whisper of influence can pass between these branching realities, can we truly call them separate universes? Or are they more like rooms in an infinite mansion, each with its own decor and drama, but all connected by hidden passages in the walls? While this remains a highly speculative frontier, it challenges our deepest assumptions about isolation, suggesting that the multiverse may be far more interconnected than we ever dreamed. A black hole is not merely a cosmic vacuum cleaner. It is a puncture in the fabric of spacetime, a place where the rules of reality as we know them break down completely. Within its event horizon, the point of no return, the path of every particle leads inexorably inward toward the mysterious singularity at its core. This one-way nature suggests a finality, an endpoint. Yet, some of the most intriguing solutions to Einstein's equations of general relativity paint a very different picture, transforming these gravitational monsters into potential gateways. The key lies in a theoretical structure known as an Einstein-Rosen bridge, or more commonly, a wormhole. Think of our universe as a vast, flat sheet of paper. A wormhole would be like a tunnel that connects two distant points on that sheet, creating a cosmic shortcut. But the mathematics allows for an even more incredible possibility. That tunnel might not simply bend back to our own sheet of paper. It could instead connect to a completely different sheet altogether, a separate universe with its own history and physical laws. This is the tantalizing prospect that a black hole could be one end of a bridge to another reality. The renowned physicist Kip Thorne, a leading expert on these structures, clarified a crucial point. Wormholes are a valid solution to Einstein's equations, but they require exotic matter to be stabilized. This exotic matter is not something we can find or create in a lab. It is a theoretical substance with negative energy density, something that would push space apart rather than pulling it together. Without this bizarre material propping it open, the wormhole would snap shut instantly, crushing anything attempting to pass through in a fraction of a second. The challenges do not end there. Even if stabilized, the tidal forces near the entrance would be unimaginably violent, stretching any object into a stream of individual atoms. Then there is the black hole information paradox, a profound puzzle at the heart of theoretical physics. Quantum mechanics insists that information cannot be destroyed. But if something falls into a black hole, which then evaporates over eons via Hawking radiation, what happens to the information that object contained? One compelling resolution suggests that the information is not lost at all. Instead, it is ejected into a baby universe, a new reality that branches off from our own, carrying that information into a completely separate cosmic domain. In this view, every black hole could be a creator, giving birth to its own cosmos. Picture an ant walking on a folded piece of paper. The direct route from one point to another is a long, arduous journey. But if the paper had a wormhole tunnel connecting them, the ant could pop through in an instant. Now, imagine that tunnel does not lead to another point on the same paper, but to a drawing on a completely different canvas. That is the staggering potential of a black hole as a gateway. If these cosmic structures are not final graves but one-way tickets to new realities, does that make them the ultimate explorers, the universe's own method of seeding existence? The physics of black holes remains one of the most active frontiers, a place where the colossal gravity of general relativity smashes into the probabilistic weirdness of quantum mechanics, and the answers we find there may finally reveal our connection to an infinite multiverse. Your sense of a continuous past may be the most fragile illusion of all. This unsettling possibility lies at the heart of the Boltzmann brain paradox, a thought experiment that pushes multiverse theory to its logical and philosophical brink. The puzzle is named for the 19th century physicist Ludwig Boltzmann, who pioneered our understanding of entropy, the natural tendency of systems to move from order to disorder. Boltzmann himself wrestled with cosmic implications, once pondering how the immense order of our universe could arise from chaos. In an eternally inflating multiverse, where time and space stretch toward infinity, random quantum fluctuations can theoretically assemble anything, given enough opportunities. The statistics are brutally counterintuitive. The probability of random fluctuations spontaneously forming a single, self-aware brain, complete with fabricated memories of a life that never happened, is astronomically higher than the probability of those same fluctuations painstakingly building an entire 13.8 billion-year-old cosmos with galaxies, planets, and a consistent history. Forming a whole universe requires an enormous, sustained drop in entropy, a move from disorder to profound order. Assembling one lone brain for a single moment is, by comparison, a much simpler and more likely accident. Picture a Boltzmann brain as a consciousness that flickers into existence for just 1 second, floating in the void. In that fleeting instant, it possesses a fully formed memory of reading this sentence, of a childhood, of loves and losses, all of them utterly false. Then, just as suddenly, it dissolves back into the random chaos from which it came. How could you ever prove you are not that brain, experiencing this very moment as its one and only conscious thought? This is not just a bizarre fantasy. It is a major philosophical problem that forces cosmologists to scrutinize their models. If a certain version of the multiverse predicts that Boltzmann brains should overwhelmingly outnumber ordinary observers like us, then that model has a serious flaw. Why are we part of a vast, ordered cosmos and not just a momentary flicker? One proposed resolution is that our universe began in an exceptionally low entropy state, a special initial condition that made our long, structured history possible. Another suggests that in the true multiverse landscape, there are still more bubbles like ours with stable laws and long histories than there are random Boltzmann brains, so it is still more likely we are ordinary observers. This paradox forces a humbling conclusion. Our most fundamental assumption that our memories reflect a real past becomes a piece of data that any complete theory of the cosmos must ultimately explain. Our own minds may be the final frontier we cannot cross. The human brain, a 3-pound organ forged by evolution to solve problems on an African savanna, now strains to grasp realities beyond space and time. We are confronting a profound epistemological challenge, a fundamental limit on what we can know, not because of our tools, but because of our very wiring. The philosopher Immanuel Kant argued that our pure reason operates within the fixed categories of space, time, and causality. We can never know the world as it is in itself, the noumenal world, only as it appears to us through these mental filters. Our cognition is exquisitely tuned for what we might call the middle world. We are experts at judging the trajectory of a thrown spear, recognizing a face in a crowd, or navigating a forest path. Our intuition is built for medium-sized objects moving at moderate speeds, a reality governed by classical physics. This is why the probabilistic blur of the quantum realm and the infinite stretches of the cosmic multiverse feel so deeply alien. They violate the core rules our brains use to construct a coherent reality. To bridge this gap, we have developed powerful workarounds. Mathematics provides a formal language to describe what we cannot visualize, allowing us to reason precisely about 11 dimensions or quantum superpositions. We lean heavily on analogies, comparing the multiverse to a bubbling pot of water or a vast library. Yet these are only crutches. A bubble universe is not wet or hot, and a cosmic library does not have shelves. The analogies eventually break down, revealing the chasm between our models and the reality they attempt to describe. Consider the mind of a dog. You could train a dog to perform incredible feats, but you could never make it understand the principles of quantum mechanics. Its brain simply lacks the neural architecture for such abstract, relational concepts. The dog lives in a world of sense, sounds, and immediate needs, a reality just as real as ours, but fundamentally limited in scope. Are we, in our quest to understand the multiverse, like that dog? If we were one day presented with a definitive, airtight mathematical proof of intersecting realities, would we truly comprehend it? We might be able to manipulate the equations and make accurate predictions, but would we possess the mental capacity to internalize its meaning, to feel the weight of an infinite cosmos in the way we feel the warmth of the sun? This is not a surrender of curiosity, but an honest acknowledgement of our place in the cosmos. Recognizing our cognitive boundaries is a vital act of intellectual humility, a necessary step in the sincere pursuit of truths that may forever lie just beyond the horizon of our understanding. The laws of physics feel as permanent as the stars, but the multiverse suggests this is a grand illusion. We have long searched for a single, elegant set of equations that would explain everything, a final theory of the universe. Yet the multiverse framework offers a radical departure, proposing that the laws we observe are not fundamental truths written into the cosmos. They are local bylaws, accidental features of our particular cosmic neighborhood. Physicist Lee Smolin captured this paradigm shift, stating that the laws of nature are not fixed, they evolve. This idea demotes our sacred constants from necessary truths to environmental contingencies, a cosmic accident frozen in time. The true fundamental reality is not the specific laws themselves, but a single, overarching meta-law. This could be the wave function of the universe in quantum cosmology, or the vast landscape of possible vacuum states in string theory. This meta-law does not dictate one specific reality. Instead, it generates a sprawling menu of possibilities, a cosmic catalog of every possible way a universe could be structured. Our universe is simply one entry in that catalog, with its particular strength of gravity and mass for the electron. The mechanism that selected our specific entry from the menu likely involves a cosmic phase transition in the fiery first moments of the Big Bang. Think of the early universe as an unimaginably hot, symmetric state where all forces were unified and indistinguishable. As the cosmos expanded and cooled, it underwent a series of symmetry breaks, much like water freezing into ice. Water's fundamental nature is always H2O, but its appearance as solid ice, liquid water, or gaseous steam depends entirely on local conditions like temperature and pressure. In the exact same way, the underlying meta-law of the cosmos remains constant, but the low-energy physical laws we experience were determined by how the primordial fields settled into their specific, stable state as the universe cooled. This local vacuum state is what we now measure as the laws of physics. This stands in stark contrast to the traditional view, which holds these laws as immutable and universal, the same in every corner of reality. If they are merely local and accidental, it forces a profound question. If the laws are just a random draw from a near-infinite deck of possibilities, does that remove any sense of purpose or design from the cosmos? Or does it instead instill a deeper sense of wonder at our incredible luck, that we find ourselves in one of the rare universes where the numbers allowed for galaxies, stars, and life to form? This perspective fundamentally reshapes the quest for a final theory. We are no longer searching for the one unique set of equations that describe everything. We are searching for the single, generative meta-law that births an infinity of cosmic possibilities, with our reality being just one beautiful, fleeting expression. The universe might be built not of atoms, but of answers. At the heart of quantum mechanics lies a fundamental unpredictability, a realm where particles exist as clouds of probability until a measurement forces a definitive outcome. This process is not just a physical event, it is an informational one. The universe seems to be asking a continuous stream of yes or no questions. Is the electron here? Is it spin up? Each answer, each bit of information, crystallizes a piece of reality from a haze of possibilities. This is the essence of the It From Bit Doctrine, a profound idea pioneered by the visionary physicist John Archibald Wheeler. He captured its radical nature by stating, "It from bit symbolizes the idea that every item of the physical world has at bottom, at a very deep bottom, in most instances, an immaterial source and explanation." In this view, the particles, forces, and even the fabric of space-time are not the primary reality. They emerge from something more fundamental, a cosmic stream of information. This perspective offers a stunningly unified language for the entire multiverse. Whether we are discussing the branching worlds of quantum mechanics, the bubbling universes of eternal inflation, or the mathematical structures of Tegmark's ultimate ensemble, each can be seen as a distinct informational pattern. The multiverse, then, is not a collection of places, but a vast and varied library of programs running on a cosmic computer. Each universe is a unique software execution, defined by its initial code and the logical rules it follows. Picture a cosmic Wikipedia page that describes you. The text on that page, the information about your height, your memories, your very composition, does not just describe you. In a very real sense, it is you. If someone were to edit that information, your reality would change instantaneously. This is not just an analogy for our digital age, it is a potential metaphor for the foundational layer of existence. The holographic principle we explored earlier fits perfectly within this framework, suggesting that the information for our entire three-dimensional universe is painted on its two-dimensional boundary, like a perfect, lossless compression algorithm for reality. This informational lens forces a deeply personal and reflective question. If the reality we perceive is woven from abstract data, what does that imply about the consciousness that perceives it? Is your mind, your sense of self, simply a particularly sophisticated and self-referencing information processing system, a unique pattern temporarily running on the hardware of your brain? The informational viewpoint does not diminish the wonder of existence, it reframes it. It suggests that all the intersecting realities we have journeyed through, from quantum branches to simulated worlds, are ultimately different expressions of a single, profound truth, that at the core of everything, from the smallest particle to the grandest cosmos, lies the pure, transformative power of a single bit. The silence of the cosmos is a profound puzzle. We have scanned the skies for decades, listening for a whisper of another civilization, and heard only the natural hum of the universe. This is the Fermi paradox, the haunting question, where is everybody? The multiverse does not just add more places for aliens to hide. It completely transforms the nature of the question itself. The Great Filter hypothesis suggests that somewhere between the emergence of life and the rise of a galaxy-spanning civilization, there is a wall, a step so difficult that almost every potential civilization fails to pass it. In a single universe, we are left wondering if that filter is behind us, making us the rare first success, or still ahead of us, spelling our doom. But through a multiversal lens, the Great Filter might not be a universal law at all. It could be a local condition, a feature of our specific cosmic environment. Our universe's particular blend of physical constants might have set the bar for intelligent life impossibly high. Perhaps the strength of the weak nuclear force in our cosmos makes the step from single-celled organisms to complex, multicellular life a monumental fluke. Or maybe the specific value of the cosmological constant makes interstellar travel so impractical that civilizations are forever stranded in their home systems, silently flourishing and dying alone. In another bubble universe with a slightly stronger electromagnetic force or a weaker gravitational constant, the transition from stardust to sentience might be as common and inevitable as the formation of stars themselves. That universe could be a cacophony of overlapping transmissions, a galactic internet buzzing with the conversations of countless species. Astronomer Jill taught us insight that the search for extraterrestrial intelligence is a search for context takes on a staggering new meaning here. We are not just searching for other beings, we are searching for our universe's own biography, trying to learn if our physical laws are a recipe for solitude or community. This reframes the entire paradox. It is no longer a question about our universe, but a question about our universe's specific address within the multiverse. Consider the possibility of a cosmic United Nations, a gathering of delegates from different bubble universes. Our universe's delegate would sit in a quiet corner with little to report. We have one species on one planet, just beginning to tap the resources of a single solar system. We are the quiet, backwater province in the infinite metropolis of realities, a place other, more connected civilizations might fly over without a second thought. This leads to a deeply unsettling reflection. If we finally confirm that we are utterly alone in our observable universe, does that make our existence uniquely precious, a single, fragile flame in an immense darkness? Or does it simply mean we were unlucky, born into a sterile branch of the multiverse where the dice rolled against the emergence of cosmic company? The silence we hear may not be a sign of our rarity, but a signature of our cosmic isolation, a direct consequence of the local laws that gave us birth. This perspective does not end the search, it ignites it with a new purpose. If advanced civilizations do exist in other realities with more permissive laws, might they have developed technologies to peer across the dimensional divide? Could the strange anomalies in our cosmic microwave background be more than just collision scars? Could they be the equivalent of a knock on the door from a neighbor we never knew we had? The search for extraterrestrial intelligence is no longer confined to the stars in our sky. It has expanded to encompass the very nature of reality, asking if our lonely universe is an exception or the rule in an infinite ensemble of worlds. The human mind seems almost pre-wired for the multiverse. Our deep psychological need for these stories of other worlds may reveal as much about ourselves as it does about the cosmos. Psychologist Clay Routledge, who studies our search for meaning, notes that human beings are meaning-making creatures. We are driven to find patterns and create narratives that help us make sense of our existence, especially in the face of our own mortality. The multiverse is a powerful narrative that directly addresses some of our most profound anxieties and desires. It offers a psychological escape hatch from the terrifying finality of death through ideas like quantum immortality, where a version of you always survives. It soothes the sting of regret by suggesting that in another reality you made the right choice, took the other job, or said the words you held back. This is a direct appeal to our capacity for counterfactual thinking, the mental act of imagining alternative outcomes to past events, a process that can be both a source of anguish and a wellspring of hope. Think of someone nursing a broken heart, lying awake at night. To cope with the pain, they might comfort themselves with the thought that somewhere, in a universe just a breath away, they are still happily together. That parallel world is a mental sanctuary, a place where their story did not end. This is not so different from ancient mythologies, where gods presided over multiple realms like Valhalla or the Elysian Fields, or from religious concepts of reincarnation and alternate planes of existence. These stories have always served a similar function, offering a vision of existence that transcends the harsh limits of a single, linear life. Another powerful driver is terror management theory, which posits that much of human culture is a buffer against the anxiety of knowing we will die. The multiverse, in its infinite expanse, can feel like a form of cosmic immortality. If every possibility is realized, then the essence of you, your consciousness in some form, persists forever across the branching tree of reality. We also have a deeply ingrained tendency to anthropomorphize the universe, to project human-like qualities onto it. We search for purpose and design in the stars, and the multiverse reframes that search. Instead of a single, indifferent cosmos, we become part of an immense generative process, a grand experiment in existence where our lives, however small, are part of an infinite tapestry. This leads to a reflective and deeply personal question. Is our powerful, almost instinctual attraction to the multiverse a sign that we are intuitively grasping a fundamental truth of reality, that our minds are sensing the genuine structure of a pluralistic cosmos? Or is the multiverse merely the ultimate comforting story, a sophisticated psychological defense mechanism we have constructed to cope with the frightening finitude and crushing singularity of our own existence? Understanding the deep psychological roots of this belief is essential for a complete picture, forcing us to separate the emotional appeal of the idea from the hard, empirical evidence that might one day confirm it. For every physicist sketching a map of infinite worlds, another warns we are charting a mirage. The multiverse is far from settled science, and its most prominent critics argue it risks leading fundamental physics into a dead end. Nobel laureate David Gross gave voice to this deep unease, stating plainly, "I do not like the multiverse. I think it is a betrayal of the scientific method." To these thinkers, the core issue is falsifiability. A scientific theory must make predictions that can, in principle, be proven wrong by experiment. If the multiverse encompasses every possible outcome, then no observation can ever contradict it. It becomes a theory that is not even wrong, an idea so flexible it explains everything and therefore explains nothing. This criticism strikes at the very definition of science, suggesting that by embracing an infinite, unobservable ensemble, we are abandoning the empirical foundation that has guided our greatest discoveries. There is a growing concern that this multiverse narrative has created a kind of physics crisis, a sense that we are giving up. The original dream of physics was to find a single, elegant set of equations that uniquely describe our universe, a final theory that explains why the laws of physics must be exactly as they are. Resorting to a multiverse, critics argue, is an argument from failure. It is an admission that we cannot explain why our universe is the way it is, so we simply postulate that every possible universe exists and note that we, of course, must be in one of the habitable ones. This is seen by some as a surrender of the scientific quest, a move from explanation to mere description. Alternative research programs actively reject this path, seeking to explain fine-tuning without invoking an infinity of unseen worlds. Some theorists pursue dynamical approaches, suggesting the constants of nature are not fixed but slowly evolve over cosmic time, naturally selecting for values that allow for complexity and life. Others champion the principle of naturalness, which holds that the fundamental parameters of a theory should not require incredibly precise, artificial adjustments to match reality. A universe that is natural does not rely on miraculous cancellations or lucky numbers. Imagine our universe as a lottery ticket. Proponents of the multiverse say that with an infinite number of tickets, a winning one was bound to appear. Critics counter that simply declaring we won the lottery is not a scientific explanation. It is a refusal to look for the deeper rules of the game itself. It sidesteps the profound question of why this particular set of laws exists at all. Could our current fervor for the multiverse be a temporary phase, a placeholder for a more profound understanding still waiting to be discovered? This rigorous, healthy debate is the engine of science, ensuring that even our most captivating stories are held to the unforgiving standard of evidence. Your immediate sense of a flowing present moment is a powerful illusion. Time itself behaves in a radically different way within the multiverse framework, leading us to the block universe theory. This eternalist view proposes that past, present, and future are not a river flowing from one to the next, but are all equally real, fixed in place within a static four-dimensional structure. Reality is not a process of becoming, it is a timeless block where every event from the Big Bang to the last star's death simply exists. The philosopher J. M. E. McTaggart argued that time is unreal because our descriptions of events as past, present, or future are contradictory and cannot capture a fundamental reality. In this view, the feeling of a moving now is just a feature of our conscious perception, not a feature of the cosmos. When we layer the many worlds interpretation onto this block, the structure becomes a vast, branching tree. Every quantum decision point creates a new, permanent branch in this block, meaning every possible timeline you could have lived exists eternally and completely, written into the fabric of reality. Your life is not a single, linear path. It is an immense, unchanging tapestry woven with every choice you ever made and every choice you never did. An alternative and even more radical idea comes from physicist Julian Barber, who suggests that time may not exist at all. He proposes a timeless physics where there is only a vast landscape of nows, individual configurations of the entire universe. What we experience as the passage of time is simply our consciousness jumping from one now to a very similar one, like a needle skipping across a cosmic record. This landscape of nows could itself be seen as a multiverse, a static collection of every possible frozen moment. Imagine the entire multiverse as a single, pre-recorded movie containing every single possible scene from every possible story. Our conscious awareness is not watching the film from the beginning to the end. It is a spotlight illuminating a single, consistent track through the film, creating the powerful, inescapable illusion of a linear narrative. The film itself, however, is complete and unchanging. If all moments across all branches exist forever, what happens to our most fundamental experiences of change, progress, and the relentless march of time? The very idea of cause and effect begins to dissolve, replaced by a vast, eternal map where every point is equally real. Your birth, your most cherished memory, and your final breath are all just fixed coordinates in this cosmic block, forever present in their own branch. This forces a radical re-evaluation of reality itself, suggesting that the flow we feel is the deepest and most personal of all cosmic mirages. Undeniable proof of a multiverse would detonate a conceptual bomb at the very core of human civilization. The day scientists announce they have found the concentric rings of a bubble collision in the cosmic microwave background would be a day unlike any other in history, eclipsing the moon landing in its philosophical shockwaves. A science historian might observe that the Copernican revolution dethroned Earth from the center of the cosmos, but the multiverse revolution would dethrone our entire reality from its unique status. This would not be a discovery confined to textbooks. It would be a fundamental rewriting of our story, challenging the foundational narratives that have sustained human cultures for millennia. Across the world's religions, the immediate impact would be profound and deeply unsettling. Many faiths are built upon a singular creation story, a unique event where a divine power brought our one universe into being. The existence of a near-infinite number of other universes, each with its own potential history and perhaps even its own forms of life, would force a monumental theological reckoning. Would a creator need to be reimagined as a gardener of infinite realities rather than the architect of a single cathedral? Or would this evidence be interpreted as the ultimate expression of a creator's limitless power? Some religious frameworks might absorb this new paradigm, while others could face a crisis of faith as profound as any in history. Philosophy would confront its own existential earthquake. The confirmation that every possible version of you is living out every possible life could trigger widespread nihilism. If no choice is final and every path is taken, does any single life hold intrinsic meaning? The value of our struggles, our loves, and our losses could feel dangerously diluted. Yet, a different philosophical movement might surge in response, one of radical acceptance and liberation. The anxiety of the road not taken could vanish, replaced by the peace of knowing that all roads are traveled. Your life is not a test with a single right answer, but a unique experience to be fully felt, one thread in a magnificent branching tapestry. The technological and economic implications are equally staggering. The very principles that underpin a multiverse, like accessing the quantum wave function or the energy of the inflationary field, could inspire entirely new paradigms of computation and power. Imagine computers that harness the processing power of parallel realities, or energy sources that tap into the latent potential of the quantum vacuum. Global economies would pivot, with unimaginable investments flooding into fundamental physics and related technologies. A new space race would begin, not to reach other planets, but to find a way to interact with other universes. Picture the announcement day itself. The news breaks simultaneously across every screen on the planet. There are celebrations in some quarters, a collective awe at the expansion of human knowledge. But in others, a deep, unsettling silence falls. The global conversation fractures. Some see a universe of limitless possibility, while others see a cosmos where humanity is rendered cosmically insignificant. Would this shared revelation that we are all just one version of an infinite number of selves finally unite humanity under a common cosmic identity? Or would the sheer weight of that knowledge, the devaluation of our singular narrative, drive us further into isolation and despair? The search for the multiverse is not merely an academic exercise. It is a quest that holds up a mirror to our deepest fears and our most profound hopes for what it means to exist at all.